file with your OpenCV code, and that's called master OpenCV. Let's extract this file into, again, our home directory for easy access. Good, it's done. That's pretty quick. And now let's go back to our IPython browser, and it instantly should update to have master OpenCV. And now we can run this code. So I have all the code that you need for this tutorial. So let's just try running beginning tips, just some quick code to make sure everything is running. This shows you where your Python file is running from, where your Python is located actually. This prints our working directory. This just tests some imports, print the OpenCV version. This has not been updated to support Python 3. Alright, what I'll do before I actually give you guys this file, I'll make sure all the print statements support Python 3, because it's pretty annoying how Python 2 and Python 3 have this bracket function for print, because this tutorial was made for Python 2 actually. So now all our code here is here, so all the images, so we can just quickly just test some more stuff. Import OpenCV, import NumPy, it's a hello world file, there we go. So right, so your tutorial is fully working for OpenCV now. Thank you.
Hi, and welcome to section 2 of this course, where we're going to take a look at the basics of computer vision and OpenCV. So I will just briefly go over the topics we're covering in this section. So firstly, we're going to take a look at what exactly are images and how are they formed. After that, we're going to look at how images are stored on computers. And then after we complete that, we're actually going to get started into OpenCV and do some basic operations such as reading, writing, and displaying images, then performing grayscale operations, then taking a look at the different color spaces that we have available, and also representing images in histogram form and how you interpret that. And lastly, we're going to use OpenCV to draw some basic shapes and put text on images. Hi, so what exactly are images? Now I have a one-line definition here for images, which tells us that images are two-dimensional representation of the visible light spectrum. So what exactly does that mean? What does two-dimensional mean in this context? Now you may have a faint idea that an image can be a photograph, can be something you see on your laptop screen or TV screen, and that's exactly right. Those are all two-dimensional planes where there's only an XY dimension. And that XY dimension here corresponds to different pixel points on computer screens, or in photographs, basically dots per inch, DPI. You may have heard that in some other form, printers perhaps. And so now each pixel or DPI point reflects different wavelengths of light, and that is where we refer to the visible light spectrum. Now the visible light spectrum is part of the electromagnetic spectrum, which consists of radio waves all the way to gamma rays. And different waves here have different wavelengths. And the visible part, well, we say visible because it's visible to our eyes, consists of different wavelengths, and each wavelength corresponds to different colors, all the way from red, green to blue and slightly purple. So now in an image like this is Van Gogh's Starry Night painting. Each point corresponds to a different color, which means it reflects different wavelengths of light, which is what we see in these images. So now I hope you have a faint idea, or at least an idea of what images are. Hi, so let's talk a bit about how images are formed. So we're going to look at the most basic example of an image formation onto a piece of film. So imagine you're outside in a park and you're holding a strip of film while facing a tree. So light reflects off the tree at different points and bounces off the tree onto your piece of film. So as you can see in this example, what happens here is that the top of the tree and the middle of the tree are going to reflect at similar points along the film. That's not good. That will actually that will basically result in an unfocused image or blurred image here. So as we can see, that's not how our eyes or cameras work. This is a better example of how our eyes and cameras work. We essentially use a barrier to block off most points of the light while leaving a small gap here, and that gap here is called the aperture, and this allows just some points of light to be reflected onto the film. So this gives you a much more focused image, and it's actually the basis of a pinhole camera. Hi. So there is a problem with this simple pinhole camera model in that the aperture is always fixed. So that means that a constant amount of light is always entering this hole, which can be sometimes overpowering for the film, meaning that everything is going to look white. And secondly, we can't focus using this fixed aperture. To focus the image even better, although it's never going to be as bad as the previous image, we still need to move the film back and forth. And that's not really a good system. So how do we fix this? Well, by using a lens. And an adaptive lens, which is what most modern cameras and our eyes use, it allows us to control the aperture size. And in photography, aperture size is referred to as f-stops in cameras, and lower is better. And also lower allows us to get some nice depth of field, which is also called bokeh in photography. Just so you know, bokeh is a highly desirable trait in photography. It allows us to have very blurred backgrounds while we focus on a foreground image, resulting in a pretty nice effect. Secondly though, with using a lens, you actually can control the lens width, which allows us to, instead of moving the film back and forth, we actually use the lens to focus it directly on this point here. This results in a very nicely controlled system. So firstly, before discussing how computers store images, I think it's good to discuss how humans see images. And if there's one thing you should know, humans are exceptionally good at image processing. Starting with our eyes, they're remarkably good at focusing quickly, seeing in varying light conditions, and picking up sharp details. And then in terms of interpreting what we see, humans are exceptional at this, as we can quickly understand the context of different images and quickly identify objects, faces, you name it. We can actually do this far better than any computer vision technique right now. And our brains do this by using 6 layers of visual processing that you can see here. I won't go into the details of this, but it's incredibly complicated. And if you're curious, you can visit the Wikipedia page on our visual system right here.
So how do computers store images? Now there are many ways this can be done. However, we're going to look into the default method utilized by OpenCV, which is RGB. RGB stands for red, green, and blue. So imagine this 10 by 10 grid I have here represented an image, and at each pixel point, which is what these cells are, we have 3 values, one for red, one for green, one for blue. Now OpenCV stores these values as an 8-bit integer. 8 bits allows us to go from 0 to 255, giving us 256 values. So now we represent colors here by mixing different intensities of red, green, and blue. So as we can see in this pretty childish drawing here, all these values here are going to be white. White is represented by 255 in each color. So that's 255 for red, green, and blue. Next, if we have a green over here, pixel 04 is going to have 0 red, 0 blue, but full green. Now, how do we make colors like brown and yellow? Now, if we mix colors, as you may have done in kindergarten, I guess, you can see that by mixing red and green, you actually create yellow. Now, that's actually how we represent color spectrum using RGB, by mixing different combinations of colors of different intensities, and that's what these values are, by the way. They are color intensities. So a value of red that's low is going to be a dim, dark value, and one that's 255 is going to be a bright red, similar to this shade here. Now this picture of the Eiffel Tower, which I blurred, not actually resized, so that we actually have a very low green pixel count, you can see the individual pixels here, and you can actually see that there are different shades of yellow and brown and black. So that's exactly how we use RGB to represent images. Now I've talked a lot about how RGB is used, but I haven't talked a lot about how it's stored in a computer. So that's what we're going to look at next. So this scary looking thing here is actually how computers store images. This mess basically represents a 100 by 100 pixel image, where each point goes from 0 to 255 as we saw previously. And these are the colors the color intensities for blue, green, and red. If you're familiar with programming, you'd quickly realize that this data can be easily stored in arrays.
and that's exactly how OpenCV stores images. If you're unfamiliar with arrays, I'll give you a quick introduction before we go into any coding. First, think of an array as a table, where each cell is identified by its location, which is called its index. So in a one-dimensional array, you have one row of information, and each cell is identified by the index number, which is 0, 1, 2, and so on. In a two-dimensional array, we have multiple rows now. So now we need two numbers to identify individual cells. So imagine this cell right here with my mouse cursor over is going to be identified by position 1, 1. Think of it like an XY coordinate system. So now we move on to three-dimensional arrays, which is what we use in OpenCV to store images. So in a three-dimensional array, think of the same two-dimensional array, but with layers of stacks behind them. So as you can see, in this first stack here, we have the red values, then behind it the green values, and blue values, and so on. So what this means now is that each cell is identified by three numbers now. We have 0, 0, and a third 0 here. 0, 1, and 0 to represent the red. If you wanted to find the green value, it would be 0, 1, 1. So that's essentially how RGB images are stored in arrays in OpenCV. So what about black and white or grayscale images? Now these are actually simpler. These don't have a third dimension. In fact, they're just stored in a two-dimensional array. So instead of having multiple layers, we just have a single layer like this. And with each coordinate position, there's a value associated with it. And that value in a grayscale image basically represents shades of gray. And there are 256 shades, not 50. And as you can see here, darker colors are represented by lower values. Previously we saw white being represented by high values, and that follows suit here. So now we have a full spectrum of gray for an image. This is an image of a number 1, by the way. So what about binary images? Binary images can also be called black and white images. However, there are just two values used, 255 and 0. Binary meaning 2. So it's either max or min type system. So what exactly is OpenCV? OpenCV stands for Open Source Computer Vision and was an Intel initiative launched in 1999. Now the primary purpose of OpenCV was to consolidate a lot of the computer vision research that was being done back then. And a lot of this research was written in C++, which is why OpenCV is actually written in C++. However, there are several bindings that exist that allow us to use OpenCV in Python, Java, MATLAB, and mobile phone applications as well. These bindings are quite useful, however, they do tend to slow down OpenCV's operation. So if you want speed, use OpenCV in C++. However, using it in Python allows us to easily grasp complex concepts and use NumPy, which is a powerful data array tool in Python. So the first major release of OpenCV was actually in 2006, and the second in 2009, and third just last year in 2015. Now, in this course, I will actually encourage you to use 2.413. It's actually very new. The latest release I think was just last year. However, you can check the website. It may be a later version by the time you read this course. And it's quite stable and it's widely deployed. I remember seeing stats saying that people still, up to 60% of researchers still use OpenCV 2.413. Now, if you think there's a need for you to use OpenCV 3.x, you can go ahead and install. However, there actually are some disadvantages to using 3.0 plus. Now, some important algorithms such as sift and sif have actually been removed. You can actually manually add them back in. However, it's a bit tedious, and I'm not going to actually encourage you to do that during this course. I'll put links up, and you're free to do so as you please. If you want to learn more about OpenCV, you can go to opencv.org or check the Wikipedia page. I should also say that OpenCV 3.x actually has a lot of the modern research built into it as well. However, and bug fixes. However, if you don't think you're going to use those, maybe just stick with 2.413. So I think you're about ready to get started with programming with OpenCV and Python. So let's begin. Hi, and welcome to your first code-along session in this course. So we're finally here using OpenCV. So this code in this IPython notebook is actually going to teach you to read, write, and display images with OpenCV. Now this code is heavily commented, at least by my standards, and it is going to teach you how to do the functions I described above. So to run each block of code, you press Control Enter, or in MacBooks, I believe it's Command Enter, and we run it, and there we go. So you should see, maybe in a second or two, a 1 comes up here, and that means that the code was run successfully. So to import OpenCV into Python, if you're familiar with Python, you would know you'd have to import a lot of different modules and libraries into Python, so we can utilize advanced functions. OpenCV is called CV2, maybe because the first version was called CV1, so we import it as CV2. Secondly, we don't necessarily need to import NumPy into this first code session here, but it's also always a good habit because you never know when you actually need to use NumPy to edit image arrays. We import NumPy as NP, mainly because it's neater to write code using an NP instead of NumPy. We could have pretty much called this anything, could have called it X, however the convention in Python is to use NP for NumPy. So let's run this block of code as well. There we go. So now let's load our first image. Now if you have a one notebook open, you don't necessarily need to import CV2 again. However, it's a good habit. It avoids missing libraries and allows you to run blocks of code independently. So do it to get into the habit. So now we use the cv2.imread function to load images. Now I would have given you a folder of images that we use in this course. So the argument we enter into the imread function is the path to the image directory, the image file actually, and that returns the image here. So we're storing the first image here as input. And now to display this image, we actually call on the cv2.imShow function. Now this function takes 2 arguments. I've put all the notes in the comments here in case you want to go over this on your own. However, I will talk it out to you. So the first argument is the title that's going to be displayed on the window. So since this is your first computer vision app you're going to make in Python, let's call this the Hello World version. And the image file that we want to open is going to be the input file that we previously loaded into here. Now you would see this wait key and destroy all Windows keys. Those are not necessarily that important, however you should always use them when you're loading images. The wait key waits for you to press any key and then it closes the window. The destroy all Windows function actually is very important, otherwise it leaves your window hanging. Without this function, you would basically need to crash your Python and then restart it through kernel restart here. So let's not do that. So let's run this first code here. There we are. Here's our input image. It's a picture of the Louvre that I took in Paris when I was there a couple of years ago. And there we go. So you've loaded your first image into OpenCV. Now this is a code without all the comments. It's much neater, and throughout the course I probably will run code that looks like this. Sometimes I will comment like load image here. However, it's not too difficult to understand. I hope you guys are following this well. If there's ever anything that's unclear in my course, please hit me a message and I'll get back to you as soon as possible, perhaps within 24 hours. So now let's take a closer look at how images are stored. So now let's import NumPy as NP, and using NumPy's .shape function. .shape is actually very useful when you're looking at the dimensions of an array. You enter the array .shape and it returns a tuple which gives you the dimensions of an image. So the 830 1245 represent the 2D XY dimensions of the image, 830 being the height, 1245 being the width. and 3 being the RGB values of the image. So let's take a look at looking at the height and width of the image by actually displaying it using the print function. What we're showing here is that we can isolate the height and width of this array, which you see will be useful later on. We use int just to convert it into a simple value, because otherwise it comes up with an L here, and we put pixels here. This is just simple string concatenation, very basic Python. I hope it's not too difficult for you if you're unfamiliar. And that's it there. So now let's go on to saving images in OpenCV. We use the cv2 imwrite function, which is very similar to the, as you can see, the imread function. However, this one has 2 arguments. First argument is the name of the file that we're going to save it as. Now, anytime you're opening files or writing files in OpenCV functions, use these inverted commas to indicate that it's a string. Secondly, this second argument here is going to be the file name of the image. So as we previously loaded our image as input using an imread function, we can then put input here, and that writes the file. Now, one cool thing about OpenCV is that it actually stores in multiple formats. You can actually read in multiple formats too. JPEGs, PNGs are the most common types, but I believe we can do BMPs and a few other image types as well. So we run this, and this should be written to your working directory in Python. You can just take a look in your file explorer and you'll see it there. If it didn't successfully run for some reason, it would return a false in the output statements here. Okay, so that's it for your first basic lesson in OpenCV. I hope you guys had fun. We're going to move on now into grayscaling images. So let's talk a bit about grayscaling. So grayscaling is a process by which we convert a full color image into shades of gray, essentially what we call a black and white image. So in OpenCV we use the CVT color function here. That takes our image that we loaded here and then passes this CV2 color BGR to gray command or function here. Now what this does, it tells the CVT color function to convert the image, which was a full BGR or full color RGB image, to a grayscale image, and stores the output as a grayscale image here. So let's run this code and we'll see the grayscale image of our full color image. So that's the color, that's the grayscale, pretty cool. So now there's an actually easier or faster method of doing this. Faster in the sense that it actually takes less time to type. We actually don't need to type this line of code anymore. All we need to do is when we're loading the image using imread is to put comma and argument 0. Imread takes on several little arguments, and this is one of them that automatically converts the image to grayscale. It doesn't save any time in code, processing time, but it just saves time in typing out the code. So we run this code here and we get a grayscale image automatically. There's one thing to note about grayscaling images is that a lot of OpenCV functions actually require you to convert an image to grayscale before it actually operates on the image. And that's because grayscale images are actually much easier to process, mainly because they have less information but yet store the important segments of the image. This is actually kind of why black and white image TV actually looks fine to our eyes. We can sort of visually process and analyze everything. Color information is a bonus, but it's not always necessary. And a lot of these OpenCV functions that use grayscale images operate much quicker than if they were to use a full color image. So you may have heard the terms RGB, HSV, or CMYK. These are names of different color spaces, and what color spaces are, they're different methods by which we store images on computers. So you may be familiar now with RGB, which is how we store colors in various intensities of red, green, and blue. But there's also HSV, which is hue, saturation, and value, or intensity. And then there's CMYK, which is actually commonly used in printers, or inkjet printers. K being black, by the way. So let's talk a bit about the RGB color space. Oh wait, is it the BGR color space? That can be a bit confusing because while OpenCV uses RGB as its default color space setting, the actual order in the array is BGR of the colors. Now there's a reason for that, and that reason has to do with how computers store memory. So as you can see here, even though we're storing it in BGR format, it actually is stored in RGB format. It's a little bit complex, and maybe you can dig into it on your own time doing some research. However, it's just a cool fact to know. And just heading back into RGB, which I may have already mentioned, it's an additive color model, which means that we mix different intensities of red, green, and blue to generate different colors. And it's quite useful. You can perhaps generate any color we can see with our eyes using this model. So let's take a look at another very important color space, which is the HSV color space. HSV stands for hue, saturation, value, / brightness, or intensity. Now this color space attempts to represent colors the way we perceive it, and it stores information in a cylindrical model which actually maps directly to RGB color points. Now in OpenCV, these are the ranges that the HSV scale goes up to. So the first value is from 0 to 179, second goes to 0 to 55, and value goes to 0 to 255. You may have remembered that in RGB they all go up to 255, sorry. So you may be wondering if HSV actually generates as much colors as RGB, and that's a good question, and the answer is in OpenCV, no, because we're actually not getting all the colors mapped here. Because how this represents colors is that you go a 360-degree circle around the cylinder, but in OpenCV we only go in 2 degree increments because it's divided by 2. So which means we don't have the same granularity in HSV as RGB. However, that's okay. We don't actually lose much in the real world of computer vision. This is more for high fidelity photography that it may matter more to them. Now HSV is actually very, very useful, and it comes in very useful in color filtering. If you want to learn more about HSV and HSL, which is another similar color space, you can look at these links here. They have some very useful information. Now color filtering is actually why HSV is so useful. This is actually a representation of a cylinder for OpenCV itself. So when you're actually filtering on color, we're actually filtering on the hue part of the HSV. So what I didn't mention before was that hue is essentially color. Saturation is vibrancy of the color. So as you can see in this cylinder here, everything kind of tends to go white at the center. So at low saturation, everything is white, and at high saturation, that's when you start getting rich colors here. And value as well is brightness. So as you can see, value here, at lower ends of the value, you get dark or black colors, and then going all the way up, you start getting bright colors. So this is how HSV represents colors, and it does it almost as good as RGB, even given this limited range here. So now back to color filtering. So while the hue goes from 0 to 180, you can see that through this circle here. If we would like to filter different ranges, this diagram gives us a lot of useful information to filter. So by setting the hue from 165 to 15, you can filter on red colors here, and then setting it at 45 to 75, you're getting the greens, and similarly for blue, 90 to 120, you can get the blues here. We're actually going to do some real color filtering in this course later on, but just remember this diagram which I created here is very, very useful for color filtering. So let's actually explore these color spaces using some code. So let's load an image here, and that image was actually the Louvre picture we loaded previously. So now let's look at the BGR or RGB values of that image. So by doing this indexing here on this image array, what we're actually doing is accessing the values, the 3 values that are stored in the first pixel location, which is 0, 0. So let's run that, and this is actually the values here. So we can see the blue, which is B here, corresponds to a value of 12, green 18, and red 31. So that's pretty cool. So we can actually play with this a little more. We can actually look at more pixels here. That one didn't change much, surprisingly. Let's look at this over here, and we get some new values. Remember, this image wasn't a highly variant image, like a very colorful image, so that's why you're probably seeing small changes if you're playing with your own values here. So now let's see what happens to these RGB values when we convert it into grayscale. So let's run the first line. As you remember previously, this converts an image to grayscale, BGR to gray, and let's print the shape that we get. So previously, actually we should print the shape for the last image file. So let's take a look at what this looks like. We see A30, 1245 and 3L. Wonder what we're going to get now. Just 2 dimensions. And as you may have remembered, I told you, when you store an image in grayscale, you're essentially converting it into a 2-dimensional array. So each pixel point now, and we can look at it by doing something similar here. Let's print this. You're actually going to get one value now, which is 22. So that's actually quite cool. And we can just get more points here. Similarly, this is actually the same thing. So now you've just seen the effect grayscaling has on images. So let's take a look at another useful color space. Well, actually HSV is extremely useful in terms of color filtering. So just have the ranges for you here as a reminder. Now, remember before previously, one of the arguments of the CVT color function was color underscore BGR to gray. Now we can see it's BGR to HSV. So we've created an HSV image here, and then we're firstly going to show this HSV image. Then separately we're going to show the HSV hue channel, saturation channel, and then value or intensity or brightness channel. Now we're doing this by indexing just that specific value in the array. So by putting the semicolon here, actually colon, sorry, this is saying we want all values of the first and second dimensions. So these are the widths, the heights and the widths, sorry. And then this is actually telling us we want the hue channel only here. And similarly, this is telling us we want the saturation channel, which is the second value of this index, and the third channel is a value channel. So let's run this code, and we can actually see the individual components coming out right here. Now this isn't terribly useful for anything other than just to visualize this as an exercise. So we can see the hue channel, and the hue channel is quite dark because it only goes from 0 to 180. And one thing you should note that's important here is that anytime you use the image show function, it's trying to show the image as a BGR or RGB image. So it doesn't actually display HSV images, because look what happens when we try to display an HSV converted image. Everything is totally messed up. I mean, the general image is here, but the colors are out of whack, and it's not terribly useful for anything, at least not to my knowledge. So we can look at the value channel, and this actually looks like a grayscale of the image, and in fact it actually is, because it's a brightness. And the saturation channel also looks a bit messed up, but it's good to visualize the HSV components separately so we have an idea of what we're looking at. So we actually can do that to the RGB channel too. So by using the OpenCV split function, it's a quicker way to do it, we can actually separate the components into BGR once an image is loaded as a RGB or BGR already. And then we're going to print the shape just so we can see what it looks like. And then we're actually going to show the individual components here. One thing to note is that because we're splitting the image here, it's going to show as a grayscale image in OpenCV because it's only going to have one dimension of color. Previously we had all three, but now it's only going to take the red, green and blue and show them as various grayscale images. However, if we use the merge function, we can actually combine all of them, and get back the original image. And what about if we wanted to actually add or amplify certain colors in an image? We can do that by adding plus 100 here. It adds 100 to every value in the blue matrix. If the value was close to 255, it's going to max out at 255. We can't go past that in OpenCV. So let's take a look at this code and see how it appears. So as we can see here, these are the individual image channels. So this is blue, move it away, green, not much to look at, and red, again, not much difference to look at. Now you should note, if I had an image that had separate green, blues and reds significantly, that you would, separately, you would actually see a drastic difference. So now let's look at the merged image here. So we get back our original image by merging all three color spaces. Quite nice. Now what about by adding the 100 to blue? Now as you can see, the image has a very much a blue, well actually almost a purplish tint to it. So this is actually how color filters and colors are created. You may have noticed movies like The Matrix sort of have a green and blue tinge at different scenes. That's sort of how that's done. But what if we wanted to see these green, red, and blues as actual colors as opposed to just grayscale images? We can use the same split function. However, let's create, using NumPy, let's create a matrix called zeros. And this may be confusing to NumPy newbies here. But what we're doing right now is that, so what exactly we're doing here is creating an array of zeros that are the same shape as the original image. So if you can see, if you run this line here, which is in the array, you get this 830 by 1245 dimensions. And everything using np.zeros, this makes every element in this array zeros. So what that's useful for is that when we're actually using the zeros array here, this basically gives a layer of all zeros that fit in the same width by height dimensions as R, G, and B here. So let's run this code, and this is pretty cool. We can see that we have now individual components with the red, blue, and green tints that make up the image. So this is actually a pretty nice thing to see. So that's it for color spaces. Hope you enjoyed this section. So now we're going to take a look at histograms, which are actually a great way to visualize the individual color components of an image. And to do so, we need to import pyplot as PLT from the matplotlib library. Now this should have come bundled with your Anaconda installation. However, if it isn't, you can run a pip install of pyplot and matplotlib separately. So we load our image in as we have done previously so many times, but now we're using this CV2 calc hist function. So I've actually put what that stands for here. So you can see what calc hist actually, the function actually does. So what it does, it generates a histogram of the image we load here. Now image needs to be in an array form, which it already is, but it has to be into second level array. So that's why we need the square brackets here. Then we actually have the number of channels. So we can use, for color images, you can pass 0, 1, or 2 to get the colors respectively. And then none if you want to use a mask or not. And 256 for the histogram size. So we actually want to see the full size, so we use a full scale of 256, and then we put the range here, and this all needs to be in square brackets as well. So now to visualize the histogram, we use the ravel function, which actually flattens our image array. Now that may be an alien concept to those of you who don't know too much data analysis type stuff, but imagine it essentially takes a two-dimensional array and actually makes it into one dimension. That's sort of what Ravel does. So we use the plot hist function. I'm not going to go into matplotlib's functions here too much, but these things correspond to range and bin size as well. And then plt show, which actually shows our histogram itself. And then this one actually looked at viewing the blue alone. We could have done 1 or 2 to get the red or green separately. But to do that, we actually have to run a loop that we actually put I here in place of the 0 and actually generates all 3 on this image here. So now let's take a look at this. This here is the blue components of our histogram image. What this means here is that we have a lot of components here in maybe the 30 range. That means the bulk of our blues are basically dull blues or dim colored blues. There's also 2 peaks in blues, although that's not that significant. Maybe it could be for other images. So now let's take a look at all 3. So this is all 3 colors here in our image. And this shows the distribution of them here. So we can see this image has the most amount of reds that are, the reds are at the highest intensity in the image. Also the greens are second highest, and then the blues are the dullest in the image. Now, more importantly here, we actually can see there's very little bright colors in our image. In fact, there's a peak of red here which may correspond to either some noise, perhaps maybe not noise, but some odd small discrepancies in the image. But the bulk of it is actually pretty dark. Usually you would find for bright daylight scenes a lot of them to be peaking around here. So that's pretty interesting. So let's take a look at another image now. As I just said. So the image we're going to use is the one I took in Tobago, which is the other island of Trinidad and Tobago. It's actually the far more beautiful, pretty island, while Trinidad is the industrial, ugly island. Sorry to say so. So let's take a look at this image. These are the blues in the image here, and closing this off, these are the full colors here. So this is actually quite interesting. You actually see there's actually some dim dark colors here, then there's a slow decrease and quite even distribution, then there's a spike of green and red. Now I actually should have probably shown what the image is. So this is the image that we just loaded up. As you can see, it's quite pretty. Some nice green hills, some reds, some yellows, quite wide, nice evenly distribution of colors here. So, and then once again we can look at the separate color components. That's the blue, and these are all the colors here. So quite cool. So let's take a look at drawing in OpenCV. So firstly, we're going to create a very simple image. It's going to be a black square. And to create a black square, we actually use NumPy's zeros function to create an array that's 512 by 512 height width dimensions and has 3 layers for the BGR or RGB colors. And this is actually going to be our blank or black square. Similarly, we can actually do this without the 3 dimensions to create a grayscale image that's also black. However, they're both going to look identical, as we can see here. So now let's draw a line across our black square, and to do this we actually use the CV2 line function. So we can see this takes in several arguments here. Image, which is the blank square image or black square image we created, and then it takes into these a tuple of 2 coordinates here. This is the start position of a line, then this is the end position of a line similarly. Now these 3 values here represent the colors BGR, so this is actually going to be the color for a line. And the last argument 5 is a thickness, which we use 5 pixels here. So let's take a look at this. Amazing. So now let's draw a rectangle on our image. So similarly, rectangles are very similar to the line function in that we have an input image, we have a start position, an end position, color, and pixels. Thickness, sorry, of a line. So that's it there. So what if we put -1 here? That actually fills our rectangle with this image here. So that's pretty cool. So how about circles? Let's create a circle here. Now the circle arguments are slightly different, as in there's no start and end. However, there is a center and a radius that gives the dimensions of the circle, then color, and then similarly thickness here. We use -1 to have a full fill of the circle image here. So that's our olive green circle we created. And what about polygons? So now polygons are basically points being the vertices of each end of the polygon. So let's create an array of points here. So these are 4 points here, and we actually use the reshape function. This is some NumPy function here. So I'm not going to get too much into this reshape function here. Just remember, this is the way we polyline requires the points to be stored. So now the polyline function, which is a CV2 function here, OpenCV function I mean, takes the image, takes the points in this form. True is whether the polygon is closed or not, color of the polygon, and the thickness of a line. So again, let's run this. There, we have a weird boomerang shaped polygon that I created. So what about adding text to images? Well, OpenCV luckily has that too as well, with putText. So putText is another simple function. Takes the image again, our black square that we created, the text in a string form. These are the coordinates of the bottom left starting point. The font, and this is a list of all the fonts that I believe OpenCV has. They may have added some others, but these are the fonts that are actually shown in documentation. This is the the font size, the color, and the thickness of the font. So now let's run this and see how it looks. There we go. Hello world. Our first little OpenCV putting text function. So that's the basics of drawing images on OpenCV. It's actually pretty easy, and we'll actually be doing it a lot throughout this course. Hi, and welcome to section 3 of this course, where we take a look at image manipulations. So image manipulations cover a wide range of topics, as you can see here. However, they're all very important in understanding the foundations of OpenCV. So we're first going to take a look at some simple transforms, then do some simple operations, which includes the ever important thresholding and edge detection, which actually forms the foundation of the first mini project you're going to complete, which is making a live sketch of yourself. So let's talk a bit about transformations. So what exactly are transformations? Simply put, they're geometric distortions enacted upon an image. Now these distortions can be simple. It can be things like resizing, rotation, translation. However, there are more complicated distortions such as perspective issues arising from different views that an image was captured from. So we classify transformations into two main categories in computer vision, affine and non-affine. So let's talk a bit about affine and non-affine transformations. Now, affine transformations include things such as scaling, rotation, and translation. And the key point to note here is that lines that were parallel in the original images are also parallel in these transformed images. So whether you scale an image, rotate, or translate, parallelism between lines are always maintained. Not so in non-affine transformations, which are also known as projective and homography transforms. As you can see here, these lines are no longer parallel in this transformed image here. However, in non-affine transformations, collinearity and incidence is maintained. What is collinearity? What that means is that if all the points on this line here remain still on this line, and vice versa. It's also important to note that non-affine transformations are very common in computer vision, and they actually originate from different camera angles. So imagine you were facing this square from a top-down view. However, you begin to move the camera this way. You can imagine your viewpoint would now be skewed. You'd actually be seeing these 2 points closer together while these two further apart. That is how non-affine transformations come about. And there are ways in computer vision that we correct these, which we will come to shortly. So let's now actually implement some of these transformations in OpenCV code. So let's talk a bit about transitions. Transitions are actually very simple, and it's basically moving an image in one direction. It can be left, right, up, down, or even diagonal if we implement an X and Y translation at the same time. So to perform a translation, we actually use OpenCV's CV2 warp affine function, but that function requires what we call the translation matrix. So without getting into too much high school geometry, a translation matrix basically is in this form and takes an X and Y value as these elements here. Now what this represents here is a shift along the X-axis horizontally, and Y is a shift along the Y-axis vertically, and these are the directions each shift takes place. So images always start off being at the top left corner, and we translate it in any direction using the translation matrix here. So let's implement this in code quickly. So let's implement translations using OpenCV now. So going through line by line, I'll quickly show you what's being done here. The important thing to note is that we're using the CV2 warp affine function, and that's being implemented down here. So quickly going through, we load the image as we've done before. We extract the height and the width of the image using the NumPy shape function, taking only the first two elements of the shape array that it returns. Next, I have a line here where we extract quarter of the height and quarter of the width. That's going to be our tx and ty value in our translation matrix. That's the direction, or sorry, the amount of pixels we're going to shift the image. And we actually use NumPy float32. That actually defines the array, the data type for our translation matrix. And by using some square brackets here, we actually created our T matrix here. It may or may not be important for you to understand this, but just take note of the form of this T matrix here. So the warp affine function takes our image that we loaded in, the T matrix that we created, and our width and height as a tuple. And it actually returns the translated image. So let's actually run this and see what it looks like. Ta-da! This is our translated image here. As you can see, it shifted the image in the X direction, a quarter of the initial dimensions, and similarly for the Y dimension, but just downward. So it's important to note that we should just take a look at the T matrix to give you an understanding of what we have done here. So this is exactly what we wanted in our T matrix. It's 1, 0 in this order, and Tx and Ty. This being a quarter of the height and a quarter of the width, respectively. So let's talk a bit about rotations. Now rotations are pretty simple as well, however they are some more quirks that I'll teach you quickly. So using our favorite politician again, Donald Trump, we can illustrate exactly what a rotation is. So as you can see, it rotates about a point, and this point here in this image is the center, and it just turns the image around that point. So imagine that point as a pivot. So similarly, in our transformation, we had a T matrix. Now we have an M matrix, which is the shorthand used for the rotation matrix. Theta here is the angle of rotation. As you can see, it's an anti-clockwise angle measured from this point here. And one important thing to note is that the OpenCV function, which is get rotation matrix 2D, actually does scaling and rotation at the same time, which you will see in the code. So let's implement some rotations using OpenCV. So rotations are very similar to translations in that we actually have to generate a transformation matrix, what we call the rotation matrix here. And to do that, we actually use an OpenCV function called getRotationMatrix2D. Now this function is fairly simple as well. What you give it is first argument is the center, the X and the Y center, which corresponds to width and height. That's the center point of the image in most cases. However, you can and you are free to rotate amongst any point in the image for whatever reason that may be. This is a theta, which is the angle of rotation. Remember, it's anti-clockwise. And this is a scaling factor, which I'll bring up shortly. And we use this rotation matrix again in the OpenCV warp affine function. So let's run this code, see what it looks like. There we go. So that's our image rotated 90 degrees anti-clockwise. And you may have noticed that the top and bottom parts of the image are cropped, mainly because the canvas size remains the same. So there are two ways we can fix that. One, let's adjust the scale here. So let's put this at 0.5. There we go. However, there's a lot of black space around this image. Now to avoid that, you would actually have to put the specific width and heights of the new rotated image. So whatever you anticipate it to be, you can program it here. However, that's not often, well, it's a bit tedious to do sometimes unless you have a special case for it. There's another way we can do it, and that's by using the transpose function here. Now the transpose function, let's run this code and see what happens. It actually transposes the image 100%. Now you may not see the bottom because it's cut off from the screencasting software here. However, the image is fully done and rotated here anti-clockwise, and there's no black space around it. So this is just another easy and convenient way of rotating images. However, it only does it in 90 degrees increments at one time. So you can play around with this and actually do some cool rotations without having to actually program the width, the new width and the new height of the new canvas. So moving on to another simple affine transformation is resizing, also called scaling. And resizing, you may think is actually quite simple. However, it involves something called interpolation. And interpolation is basically when we resize an image, imagine you're expanding points or pixels. So when you resize an image from small to big, how do we find the gaps in between those little pixels? So that's what interpolation is. And I've just drawn this simple little diagram here to show you with GPS coordinates, because when you're doing GPS tracking, you actually interpolate points quite a bit. So imagine the red points are pixels, and these are the actual pixels here. Now imagine previously, before, these pixels were closer together, the red pixels. Ignore the yellow pixels and the green pixel for now. So we just have red pixels that are closer together. But now we've stretched them out, and we need to approximate the pixels in between. That's what interpolation is. Interpolation is the method we use to actually put or generate these pixels here. So as you can see in a GPS type example, going up in a straight line north, putting a pixel here is a fairly good idea. However, doing this linear meaning straight line joining between pixels, we actually don't reflect that maybe the vehicle took a corner here. Instead, the vehicle drove maybe straight to some buildings here in this dumb example. And that's a form of interpolation which we call linear interpolation. So let's talk a bit about the types of interpolations here. There's inter-area, nearest, linear, cubic, and Lanczos 4, apparently. So these are all methods, and I won't go into details here. There's actually a very good comparison on this link here. But generally inter-area is good for shrinking or downsampling images. That's actually another form of interpolation as well. Probably just what this does is it merges the pixels within the area. That's why it's good for downsampling. Inter-nearest is the fastest algorithm according to this comparison here. Linear is good, as in this case it's a linear interpolation here. It's typically good and it's the default method used in zooming. However, intercubic, which is probably what's going to generate this green point here, is definitely better. And Lanczos, or Lanczos, is actually the best. So you can check them out here. So let's actually implement